Hi, welcome back. This is Rashid. I'm excited to present the second video on this RTL2 Routing series. Okay. By the way, if you like the content that I upload on YouTube on this channel, then please subscribe to my channel. This will really help me spread the message a lot more and get more viewing, and maybe hopefully one day I can make some money from YouTube. All right. So thank you so much for that. All right, so in this video, I'm going to talk about how to set up a design library, which is typically the first stage in most of the tools, or at least the tools I have worked with. Okay, so it'll be a little bit on the setup and we will do a little bit tickling. Means we will look into the tickle language a little bit, start with the very basics one. All right, okay, let's get started. So when you open the design, sorry, you are in Unix. Okay, so you will get a shell, right? A terminal, a shell. A shell is will interpret what you type here and will give that to the operating system. So it's like it's an interface between you and the operating system, and different commands you will type here, and then you will send it to the operating system, and operating system will take care of it. Got it? So when you open a physical design tool, okay, all those tools have their own shell. So within shell, you open another shell. So if this is your Unix shell, and this is your, for example, Fusion compiler, it will be an FC shell. Okay, so you want to go from here to here. Keep in mind that, okay, there are different type of shells. For example, TC shell, bash. Each one of them is a little bit different in terms of some of the command syntax is a little bit different. Okay, in terms of features, they have some differences. That's not the topic of this video, but the capability wise, they are some different. So when you get a Unix environment, check what kind of shell you have. You can do that using this echo command on here, 0. Okay, that will tell you which kind of shell, because once you do, you might need to do some shell scripting, not for this setup, but eventually, for some of the file reporting, parsing, automating firing of jobs, or automating the start of FC shell or other shells, or whatever tool shells you have. Sometimes you need to do some automation, so it's nice to know which kind of shell you are using, and so that you can write a scripting or some of the commands for that. Maybe, no promise, but maybe I will do a kind of a quick shell scripting tutorial at some point after physical design. Okay, so you have a shell, you know which type of shell you have, then you install whatever tool. In most, if you're part of a company or a part of an institute, they will already have that setup. They will also have a setup. So once you install a tool somewhere, you have binary, then there is an environment variable path. That's where you need to put path to where the tools as binary is. For example, if it's Fusion compiler, then FC shell, there will be a binary. That binary location need to be part of that, so that when you type FC shell, it knows where is it will search within that path and will bring that FC shell for you. Okay, so you type FC shell here and you come over here. Environment variables, just think of those. There are normal variables that you can have in a shell, and then, for example, if you type xterm and it opens another shell, the variables you have here in the child one, the children of shells of this shell, those variables will be lost. But if there is a environment variable defined somewhere here, then the children shells or the new shells that you start, they will carry those environment variable. This can be handy. For example, these days, on a big huge design, you're not doing all of your physical design on just one machine. Okay, you fire jobs on different machines using a special utility, LSF or a netpad within Intel. So you some of the variables, those children shells need to inherit. Okay, so I need to have some of these understanding of what is a variable, it's a shell variable, what is an environment variable. These environment variables will be accessed within the shells in a special way. We will talk about that in tickle. Okay, so the language here is the shell language, but when you come into FC shell, for example, the language that within here will be tickle. Okay, so I'm bridging the gap. I'm giving you some sort of transition where what language is used. Okay, shell language, tickle language. So we will learn tickle language because for this RTL2 routing series, I will stay within a shell. Okay, so that is done. Then you also need to set up a license key if you have if you're not using open source. Again, the institute organization, they will have all that things set up for you. So here is what you do. You type here FC shell and you get a shell like that. Okay. When you get a shell like this is empty. Okay. There is nothing there. All right. It doesn't have any design loaded. It doesn't know about any technology. It knows nothing. Right. It knows some of the environment variables which are defined here, which are inherent there. It knows the tool commands. It knows from the tool variables. So all the tool stuff it has, but it doesn't have anything else. So here is what we need to do. Here is what we need to start a library. Okay, we need to create a library. So library is initially is a space in your memory, SRAM, where the tool in its own format will contain what designs are there. But even before you have design, you need to know what kind of technology have, what kind of standard cell libraries we have. So it needs that technology information because it needs to synthesize your design against that technology, right? And it needs to create a layout, so it needs to know all the information about the technology. So first it creates a snapshot within the memory, and once you save that lib, then that snapshot will be written on your disk storage space. So eventually it will be stored. So next time you don't have to create from start. All you do is okay, save lib, and we will go through this. But once you get it out, next time, for example, now your FC shall crash or you close it or you've gone, if you had saved that lib, next time when you start, you basically load this thing. So you don't have to go back to the scratch. The design we have will be is very small, so even if you start from scratch, it's not going to take much time. But most of the real designs are so big that you don't want to waste time on setting up all that every time you open FC shell, right? You take it to a certain stage and then you carry on from there. Okay, makes sense. Now, what is in the library? So before the library, sorry, I forgot that. So directory structure where you run these things is also important. So here is the directory structure that I followed, and you can basically do whatever you want, but it's nice to put things in a structured way so that you can remember things, you can access things, you can separate things. So the way I do is typically let's say it's my playground folder. Okay, I should have written that to waste time here, but I didn't think of that before. And I tell you, all of these videos are not scripted. So I bring certain points, certain things in my mind, and sometimes what I talk is completely different to what I had planned. So you might sometimes feel my speed is a little slow, but you're welcome to use 1.25 or 1.5x faster when you are watching this one. So sometimes the drawing things can take a little bit of time. So what I do, I create a folder here. Okay, and then inside that I have different folders. So work date, today is 26th December, so 12/26 2024. This video will be remembered for this date. So I create for every day because every day I might be playing something new. So I create a folder here. So there is another work. Tomorrow, if I come, I might start on the same one, but I might create a new one. And then I also create a folder here. By the way, Happy Christmas and Happy New Year. If I don't do another video in the next 2 3 days. Um, so I create one flow scripts. Yeah, this is where I keep all the tickle scripts for the flow. Okay. Then I also keep here, let's keep everything lowercase, design. This is where I keep our system verilog file, verilog or VHA or whatever you have. And then I keep, I can use the design, but sometime I use constraints as separate folder, and I can put T-cons, timing constraints, maybe floor plans, maybe later on UPF comes, stuff like that I can put in there. Simple, the simpler it is, better it is in my opinion. Okay, you can always create folder inside another folder for that. These are easy. Whenever I create another way, I just have to copy these design things and then I'm done. Okay, so all the technology data, now here I come. So the library that you need to create. So what I do is when I'm here, I go inside the work. Let's say today is 26. I go inside this folder, cd um, cd to playground, and then work 12/26/2024, and I'm here right now. So my present working directory is always the work inside. This is where I send. So if for example I want to access scripts there, I want to source a script, so this is what I will do. Two dots, sorry. Then I go up, flow scripts, and then whatever file that I source. Understand that? So all my scripts will be written with relative to this path. I expect there is a folder. These three folders are up. Just telling you because I will show you my actual script. So it's important to know where what I'm referring to. Good that. Okay, now question is, as I was saying, where is all the technology data? And technology data is not kept in your local folder. That is central. You're not changing it. You only have a read access to that. And that is common to everybody. This is your own personal area. Nobody else, other people can have access to, you can give them access, but you don't have to. This is your playground area, your ward area, I don't know what other words are used. So the library that we need to create, it has two components. Okay, it has, if I partition them, it has a design side. This is system verilog, your R counter design and all that. Then this is a technology side. Okay, inside the technology side, it has reference libs and technology libs. In the reference libs, you have timing libraries for all the standard cells for that particular technology. Okay, there is a layout information it needs. The layout contains, okay, so timing contains, I have covered timing libraries before. It has timing information for every standard cell, and again, what is standard cell, I've also covered. So in my video somewhere, search a standard cell library and you should be able to get that. I should have a link somewhere in the descriptions. I will see, maybe I will include it. Then power information for every standard cell, and it also has a function. There's a function attribute on every, so open the library. There is a .lib file, which is a text file. You can open it in less or vi. Okay, I typically use for read only less editor in Unix. If I have to edit something, then I use vi. So I use less, on that lab. This is a binary conversion of this one, LDB or DB. Some people use LDB, some people use direct DB. This is a binary format. You cannot open this one, but this will be open. So open that one and look what is inside. There is a common part and there is a standard cell information for every cell, and get yourself familiar with it. Watch my standard library videos and then get yourself familiar with it. You can also download 130 nanometer open source, and then look into that one. Get yourself familiar. It's very important that you understand some of the things, how the data, what data is there and how data is presented there. All right, so those are the timing libraries. These timing libraries might be available for different PVTs. Okay, P is process, V is voltage, and T is temperature. So they have timing data, power data, and that can change if your die or your chip is working on different voltage, right? So if your chip is planning to be, let's say, on 1.8 volt, right? And you want to make sure that you have a good yield and most of your dies work at that voltage, then good, you need 1 volt. Now, actually the voltage on actual standard cell might be plus minus, right? So it's nice to have some additional voltages points, less and higher, okay, where you can close your timing. So that's why I didn't explain the topic of variations, but anyway, so voltages can be different, then temperatures can be different, then process can be different. Okay, what is the process? Is single, let's say it's 180 nanometer. It's the same process, but some of your transistors or dies, overall transistor plus interconnect, can be faster characteristics compared to some others. They might have less resistance compared to some other part. So not every shape that is drawn on the wafer will be exactly similar. There will be variation because of the equipment. Some of the and some other sometime, for example, doping can be a little bit different. One material is doped a little bit higher than another one, right? No equipment, no machine is ideal. There will be certain fluctuations. So okay, I will do a variation video separately, but right now I'm just trying to give you a concept that actual drawn metals might be a little different than the metals that you were expected, okay, and those things will create different characteristics in your front end, which is the transistor, and back end, which is your interconnect, and those can have different implication on the current through the chip, and that means it can make the chip faster or slower. But before silicon is available, you don't know if a transistor will be slower and faster. And based on previous data from silicon, these libraries can be characterized in such a way that some of those parameters can be selected to model the transistor to be slow or higher. So process means some of those key technologies parameters are selected in such a way that the standard cell library you're going to use, a NAND cell for example, will have slower, and another will be independent of voltage and temperature, will be faster, okay, and those calls are process parameters. So when dies come, majority of the dies are around the typical delay. For example, if this is the number of dies and a number of dies on a typical, let's say NAND, okay, it has like an average delay is around this. So some your transistor will be, NANDs will have more delay, some will be have less delay, so majority of them will be here. But if you want a greater yield, most of your NANDs kind of all of the NANDs meet the timing, then you ensure that your design also meets timing for this very slower, very fast. So you need to consider these points, and this is why typically the process is available as a typical. So nan can have three libraries with process 1, which is, let's say, here, process 2, and process 3. And similarly, for different voltage difference, you can have a different curves. All right. So all in all, if I summarize it, these libraries can be so many, but only the delay characteristics will change and power characteristics will change. Their function is same. So you can use one typical as a target library, but then you can do a timing analysis or optimization conversion using many. But in this particular example, the discounter that I'm doing for this is I'm going to use a single PVT. It will simplify things. Okay, and you can in later on projects you can add more scenarios. So single scenario I'm going to use, single PVT I'm going to use. So we need a timing library, and the layout, we need a layout library. So we need layout formats can be a left, which is very generic, independent of the tools, I think. And all you need to know, okay, what is the bounding bus? Let's say it's a NAND we're talking about. What is the width and height? Okay, and the pins are coming at what metals and where the pin location is, and that information is in there. We don't need to know everything inside the NAND gate. Tools are going to place them together. Later on we will replace those simple, this higher abstract kind of left frame or NDMs with very detailed everything. But right now in physical design, our lowest level is standard cell, and below standard cell we are not worry too much. We don't want to load a very heavy data there. We are playing with standard cell. Our Lego pieces that we're going to build a design with, the basics, the lowest level in those is a standard cell, NAND, inverter, buffer, flip-flop, latches, and all that. All right, I think I talked a lot. So timing library or can be one of them, target library. For us these two are same. Then a layout for synopsis is an NDM format, is a binary format. You won't be able to open this and see what is inside. Previously they had a frame view, but left is a generic one. Okay, so you know about the reference lists. I think what I'm going to do is let's stop this video here. And that I will give you briefly next time what is the technology file. There's a file .tf that you need to give, and it has some technology of information. You might not be able to watch all of that, but some of it, and how designs and different versions, and I'll give you a little bit of the tickle variables and all that, and how to then create that library inside the vendor tool that I'll show you next time. So let's stop it here. Part 2 of this library step will come in the next video. And until then, take care of yourself. Bye.